Chapter 3, Number 55. The pilot of an airplane wishes to fly due north, but there is a 65 km/h wind blowing towards the east. In what direction relative to north should the pilot head her plane if its speed relative to the air would be 350 km/h? And then draw a vector diagram that illustrates your result from part A. And if the pilot decreases the airspeed of the plane, but still wants to head due north, should the angle in A be increased or decreased? So if the pilot wants to head due north but is being blown eastward, then the plane is going to have to go some angle west of northward. It won't be able to head due north. You'll have to head somewhat westerly. And the way to do this, to see this, how this will fly out, is that we want the air to be going in this direction, where that's the speed of the air to the ground, and we're told that it is 65 km/h. And we would like the plane relative to the ground to go due north. So that's the plane relative to the ground. And I don't know what that speed will be, the so-called ground speed, but I do know that it has to point due north. And then finally, we have where the pilot actually heads out, which is the velocity of the plane relative to the air. The relative velocity equation tells us that the velocity of the plane relative to the ground is equal to the velocity of the plane relative to the air plus the velocity of the air relative to the ground. And one thing to kind of note that comes out here is that you can kind of figure out who goes where by noticing that there's an intermediary that we can get rid of. Essentially, we're getting rid of the air as a reference frame by adding it in this way. So if we look at this sort of just graphically, we would have this plus this has to go due north. And we're looking for this angle, and we're given that this is 340, but this is 65. And so since we only want the direction, we can say, oh wait, the sine of theta is the opposite divided by the hypotenuse. That's sine. So I'm going to say, because that's what I have, so I'll have 65 over 340. And therefore theta is the inverse sine of 65 over 340, which turns out to be 11 degrees. Notice that our construction already pointed out it's going to be 11 degrees west of north. 11 degrees west of the north line, which is what we sort of had before. All right, and then part C says if we decrease the airspeed of the plane but still has to head due north. So let's go and see what that's going to be. So I'm going to leave the other one up for comparison, and I'm going to say, well, we still have the 65. That has to go that way. But now we're talking that the hypotenuse is smaller. So I need this to be a smaller distance. So maybe something like that. And then, of course, I still have that they add to that. And now I'm just going to zoom out a little, keep all the sides parallel just to zoom out. And we'll have something like that. And then this one. And then this one. And we'll have angle phi. And we can see pretty clearly that angle phi has to be larger than theta. It has to be even more west. And the reason for that is, since I have less speed to work with, but I still need to cancel out the 65, I need to make sure that more of my vector points in the westerly direction, because I have less to work with, so I need to have more of it point that way to compensate. So that's sort of a way to look at it. You could also sort of just walk through now and start saying, well, you know, let's pick some random number and say, what if it had instead been, 170, but this is still 65, and then we have that phi is the inverse sine of 65 over 170, and that turns out to be 22 degrees. Kind of almost, don't get too worked up about the factor of 2 thing, because sine is sort of linear when it's low, but it's not always linear. But we can see that we need a wider angle to compensate for the slower speed.